All right. So like I said, good preview heading into what some of the questions could look like on our quiz, and that is where we are just handed some matrices, asked to do some things like scalar multiplication, adding and subtracting, multiplying. Reminders on some of these: when you do your scalar multiplication, that needs to go and multiply every term that is inside your matrix. Order does matter as we set these up. So I would do 2 times matrix C. Oh, we are way out of orientation here. Let's try this again. 2, there we go. 2 times matrix C means I'm going to go through all of matrix C and multiply every term by 2, which would be -2. 0 times 2 is still 0. And we're going to subtract 1/2 times matrix B, which means I'm going to go through and multiply every term by 1/2. But then here's again my practical advice to you is that subtracting is when we tend to make mistakes. And so I will always change a subtraction problem by distributing the negative, kind of like it's a -1, to every term inside my matrix. Okay, we tend to make less mistakes that way. And now I am adding terms. One thing that frequently happens with these is if it's the same number, we need to slow down and think about what I actually get when I put those together. So -2 plus -2 is -4, right? A lot of times people would say 0 at that point. So just make sure that we slow down on that one. 0 plus -1/2 would be -1/2. 0 plus 3 would be 3. 2 plus 1 would be 3. Questions on that first one? Second one, we do need to do, well, it is a lot easier to do the addition part first. Yes. After I just said, be careful. Wow. Is it going to be that kind of a day, huh? This could be rough, guys. I just talked about how we have to be careful with our adding and subtracting, and then I did not. Okay. Next one. We could distribute the matrix A through, but that's going to end up giving you a lot more work. So I would strategically add B plus C first and then do the multiplication part second. So I'm going to hang on to A. And do B plus C. Remember, B plus C is just adding corresponding elements. So 4 minus 1 would be 3. 1 plus 0 is 1. -6 plus 0 is -6. And -2 plus 1 is -1. And then we have to make our decision on, can I do my multiplication? So this is a good time for us to remind ourselves to how we find the order of our matrices and what that means about if we can do our multiplication. Our order is number of rows by number of columns. And when I sit those next to each other, I need my inside values to match in order for me to be able to do multiplication. And we can on this one because the 2's on the inside match. And so my multiplication becomes my rows times my columns. And my answer should be a 3 by 2 matrix. So doing that, 0 times 3 is 0. 2 times -6 is -12. And then I do that first row times the second column. 0 times 1 is 0. 2 times -1 is -2. And we move down to our second. Let's see if I can move this. Oh, not really. Second row, and repeat that process. So -1 times 3 is -3. 3 times -6 is -18. -1 times 1 is -1. 3 times -1 is -3. 1 times 3 is 3. 0 times -6 is 0. 1 times 1 is 1. And 0 times -1 is 0. Which cleans up to, let's see, -12, -21, 3, and -2, -4, 1. Questions on anything up there? Order, being able to multiply, process of multiplication. Okay, last one, addition. And we didn't get to necessarily see this on that day, but we saw it in our assignment, is that when we do addition, they need to be the same order. We cannot add a 3 by 2 to a 2 by 2 because we don't have all corresponding elements. So part C, we should have said not possible or undefined. Any questions on the review part? All right. Today, we are going to look at more options of how we can solve systems using matrices. And in order to do that, we have to be able to find the inverse of a matrix, because that's how you solve equations, is using the inverse operation or the inverse of a matrix. And so we have a little bit of steps working our way up to that process. Okay. First of all, what we are looking for two things to be inverses of each other, two matrices to be inverses of each other, is that when I multiply them together, I get what's called the multiplicative identity matrix. And that is the matrix that looks like this, with that diagonal of 1s and then everything else is 0. What happens is, if I were to take this multiplicative identity matrix times any other 3 by 3 matrix, something like this, I would not change that matrix at all. If you were to go through and do that whole multiplication process of that 3 by 3, you would get the exact same matrix that you started with, because it is the multiplicative identity, means it does not change. Okay, that's what this is talking about. And conversely, if two things are inverses of each other, we would get the multiplicative identity when we multiply those together. So you can see here by a 2 by 2, it doesn't matter which order you multiply them in, which is unique to matrices, right? Because usually switching the order does change our answer, but with the identity matrix, it does not. Questions so far? So a multiplicative inverse of a matrix is the matrix that if I were to multiply them together, matrix A times its inverse, the result is the identity matrix, the matrix with just a diagonal of 1s and everything else is 0. And if they really are multiplicative inverses, the order that I do that in will not matter. And it's this fact that we will double check to make sure that two things, or to see if two things are inverses of each other. The symbol for an inverse is the same symbol we've used all year, which that little raised to a -1. And we read it just like we have all year, A inverse. And so one of the things, we'll kind of have it one of two ways, which we have had all year, is asking if two given things are inverses of each other. And that is checking this process, that when I multiply them together, I get the identity. And when I flip the order, I get the identity, right? And we did this with functions and composition back first semester. So that is one of our two ways. Well, the other way will be just finding inverses. But first of all, it's asking show. Show that the multiplicative inverse, that B is the multiplicative inverse of A. When it says to show that, you must do A times B and B times A. You actually have to show the multiplication. And remember, when we're proving, we should maybe show more than when we're just like doing a problem and figuring it out, because the whole show part is our proof, right? When we do these two things, we should get the identity matrix. We should get a matrix that just has a diagonal of 1s with zeros everywhere else. Okay, so let's do that. Let's start with A times B. Because the entire point is to show, we will do a little bit more work than we might have if I was just doing the multiplication, and maybe I can do some of the calculations in my head. But because the whole point is to show that this is actually true, I need to show the multiplication process. So -1 times 5 and 3 times 2, right? First row times first column. First row times second column, -1 times 3 and 3 times 1. Second row, first column, 2 times 5 and -5 times 2. Second row, second column, 2 times 3 and -5 times 1. You have to show some intermediary step. You could clean those up a little bit, but at some point you have to show a little bit of an intermediary step between the multiplication and then the answer. Well, our answer, this is -5 plus 6. -5 plus 6 is 1. -3 plus 3 is 0. 10 minus 10 is 0. 6 minus 5 is 1. And we get that identity matrix. Questions? Especially because doing the opposite order of multiplication does not mean we get the same answer. You do have to show both directions. So we would do B times A as well. Okay, I'm going to give you guys a second to do B times A ahead of me. So you do, when we do multiplication, you do first row times first column. You do first number times first number. So it'd be -1 times 5, yep. And then plus 3 times 2. Okay. And then we repeat that process with every combo of rows and columns. So then I do first row times second column, and that's where these numbers are coming from. Does that make sense? So the first matrix is always, we look at the rows, and the second one is columns. Okay. Mm-hmm. All right. Now, assuming that these really are matrix, inverse matrix, we should expect that identity at the end, but our work needs to prove that. So again, let's do our multiplication here. So I start with my first row in multiplication, and this was from day 1, Monday. So if you are forgetting multiplication, go back and watch that. Times first column. First element times first element would be 5 times -1. Second element times second element would be 3 times 2. And then I can stick with that first row, but go to my second column here. First element times first element is 5 times 3. Second element times second element would be 3 times -5. And then we go back and do second row times each of our columns. 2 times -1 plus 1 times 2. And 2 times 3 plus 1 times -5. And again, that work should support the fact that we get to the identity matrix, and I can double check that. That would be -5 plus 6 is 1. 15 minus 15 is 0. -2 plus 2 is 0. 6 minus 5 is 1. This is the show part, right? Questions? Okay, so like I said, with inverses, there are basically 2 different questions we can have. Show means you must do both. A times B and B times A, and you must get to the identity matrix. Then there's also the just finding an inverse. Well, to do that, we need this number called a determinant. A determinant is a number okay, it is just a number that is a value from the elements of your matrix. And it always comes from, well, in a 2 by 2, taking A times D minus C times B. And it will give us some number. And it'll tell us about our matrix. First of all, if our matrix even has the ability to have an inverse. And second, it helps us find that. You can see determinant of A this way. Some places will mark determinant of A as looking kind of like an absolute value symbol. Okay, I think this book uses, but I want you to see all of the different ways that it can be represented. Determinant. So finding the determinant of a given matrix, again, is going to just be a number answer. And it is A times D minus C times B, or your diagonal from left, top left down, minus diagonal from bottom left up. So our determinant would equal 10 times 5 minus 6 times 9. Determinants can be fractions, they can be negative numbers, they can be 0. 0 is a number, okay? Understanding what the determinant gives us here in a few minutes will mean something to us, okay? Let's try the second one. Be careful with your positives and negatives on this because it is first diagonal minus, and then the second diagonal has a negative in it also, so just be cautious with your positives and negatives in that, okay? Minus a negative 15 would be plus 15. Check my mental math on that, negative 17. Questions? Okay. So this is one of the things you will look at of a matrix, and really its purpose is leading us towards finding its inverse. Because the determinant shows up, and I know this is a lot of stuff up here, but the determinant shows up in the process of finding the inverse. So if we have a matrix here, A, B, C, D, and this is only for a 2 by 2, our process will change with a different size matrix. But a 2 by 2, your inverse can be found by doing 1 over that number we just found on the last page. So 1 over your determinant, and then look at how these things switch. A and D just flip-flop spots. C and B get the opposite sign. Okay, so if I were to take this matrix that started out as A, B, C, D, and I'm in the process of getting the matrix, the two things that I would do would be to exchange those two values and then take these two values and multiply them by a negative 1. They stay in the same spot, but get multiplied by a negative 1, okay? So however you want to look at this, we have there, you can put it as your formula here. That was the formula for the determinant, or just know that it's 1 over your determinant. But look ahead. I said that the determinant can be any number, right? Including 0. What would happen if our determinant was 0 and I was supposed to put it in the bottom of a fraction? Undefined, right? And so what that tells us is, a little note, is if the determinant of your matrix equals 0, no inverse exists, you cannot find the inverse of that matrix. So you'll notice again that it'll always say find the inverse if possible, and this is the time that it's not possible. When your determinant is 0, that is the one time you will not be able to find the inverse of that matrix. Questions? And again, hopefully that makes sense because it ends up being the denominator of that fraction, and we can't have a 0 in a denominator. So we can't have a determinant of 0 and still find an inverse. So the second question about inverses, remember the first one was to show that two things are an inverse, multiply A times B and B times A and get your identity. The second question around inverses is to find it, to just, here's a matrix, find its inverse if possible. And again, that if possible is if your determinant is equal to 0, it is not possible, right? So we always have to keep an eye out for that. I think it'll kind of take care of itself as we do that. So if I go off to the side and I just find the determinant of A to see if I can even do the inverse of this, our determinant is A times D minus C times B and it looks like we're getting a determinant of 1 that we can do. Okay, so now I take that determinant, and to find my inverse, I'm going to do 1 over that determinant, which was 1. And then remember how we're going to alter where these are or how they look. One of the things I will do is exchange A and D. Just flip them. The other thing I will do is multiply B and C by a -1. But they stay in the same spot. And the last thing we're going to do is multiply that scalar multiple through, which is not going to look like it does much on this one because our scalar multiple is 1, which is not going to change anything. Okay, but I do take that 1 and I distribute it to each of my terms, and our inverse then ends up being 1, 2, 1, 3. Questions? Okay, let's try one more. Find the multiplicative inverse if possible. Oh, I will say sometimes these end up with some kind of ugly fractions in them, and that's okay. To be expected when I have to maybe be distributing a fraction through. All right, our matrix is 6, 3, 2, -1. Careful on this one. What is our determinant? -12, right? So do we have an inverse? Yes, we do. So that will go to the bottom of our fraction, which we will distribute that -1/12 through, switch A and D, change the sign on B and C. And now I'm going to distribute that 1/12 that is sitting outside here to every term and simplify. A negative times a negative is a positive. A negative times a negative is a positive on that -3. But what is 3 over 12? 1/4. Same thing, negative times a negative is a positive. And what is 2 over 12? 1/6. And this time is a negative. And 6 over 12? 1/2. There is your multiplicative inverse. Since we're looking at this same page, what if I were to alter one of those and instead of having -1, we had +1? Does anyone see what that's going to change? Yeah. What am I making happen right now? No inverse, right? No inverse, because I just made us have a determinant of 0. And so if this happens, there is no possible inverse, right? That's what you're looking for, is a determinant of 0, no inverse. Questions? All right, the determinant of a 3 by 3 is a little bit more involved. There's obviously more numbers. And so what we can do is we can break it down into 2 by 2 determinants. And we already know how to do a 2 by 2 determinant. And then you just have to multiply it by one more number. Let me show you where those are all coming from. You basically focus on the first column. In the first column, a color that's going to stand out here, that this first term right here comes from your first number in that first column. If you cross off everything that term is involved in, so if I were to go like this, do you see what's left over? This bottom 2 by 2 is this. Okay, so if I cross off everything that A1 is involved in, its row and its column, the 2 by 2 that's left over is the 2 by 2 we'll use to find the determinant to multiply by A1. With me so far? So this ultimately would become A sub 1 times the determinant of this 2 by 2, and we already know how to do that. B2C3 minus B3C2. Okay, it's the determinant of that little 2 by 2. And then we repeat that process. So now I'm going to look at the second number, and it's all based off of the first column. Again, if I were to cross off everything that is involved in, the things that are left over make up the 2 by 2 that we're going to multiply it by. Okay, so A2 gets multiplied by the determinant of that matrix. And the determinant of that matrix would be B1C3 minus B3C1 with a subtraction between them. And finally, the last number in that first column, cross off what it's involved in, its row, its column. The leftovers is the determinant, or is the 2 by 2 that we'll find the determinant of. So A3 will get multiplied by B1C2 minus B2C1 with a plus between them. Now, this does take a little bit of remembering, mostly the alternating subtraction and addition. Okay, so you will have to remember a little bit. You already know how to do the determinant of a 2 by 2. And so doing it this way kind of gets us that process. Again, questions? Okay, let's try one together. So the first thing we're going to do is, it's all based off of this first column. Let's create our little 2 by 2 matrix. So it's going to be 6 times the determinant of this matrix. So the determinant of this matrix will be -5 times 0 minus 2 times 3. Oops. Okay, keep in the first column. Remember, now it's going to be a minus. And then -3, let's cross off what it's involved in, times the determinant of 4, 0, 2, 0. So A times D would be 4 times 0 minus C times B. We all doing okay so far? Remember, subtract. And then our last one, we will add. One times the determinant of what's left over when we cross off its row and column. 4 times 3 minus -5 times 0. And then all we have left to do is clean that up, which again is why I may suggest a scientific calculator, right? Or hope I get through my mental math okay here. So this would be 6 times 0 minus 6 minus a negative is plus. 0 minus 0 is 0. Plus 1 times, and let's see, this would be 12 plus 0 is 12. Which ultimately gives me -24. Questions? No? I know that it's a little bit of a process on the 3x3, so it might take a little bit of time as reminding yourselves of how we do that. Use your first column, cross them off, find the determinant of what's left over, and then remember you're alternating, minus then plus. Okay. All right, let's try one without me walking you through it on our check for understanding. Again, if you need to flip to that back page where you've got some extra white space, go ahead and do that. Because I don't think we have a check for understanding in our notes packet.